We present the multi-object rearrangement with Monte Carlo Tree Search to address the planar non-prehensile sorting task. Rearranging objects, for example, to clear a path or clean a table, is an essential skill for an autonomous robot. The robot needs to plan in which order and where to move the objects. This rearrangement planning problem is known to be NP or even P-space hard, depending on the goal definition. In this work, we are interested in large-scale non-prehensile rearrangement problems, where a robot pushes multi-objects simultaneously to reach a goal that is characterized by the final poses of many objects. Specifically, we consider the planar non-prehensile sorting task as illustrated. Here, a planar infactor has to sort objects belonging to different classes into homogeneous distinct clusters. The problem is challenging as it's non-monotone, requires multi-objects pushing to be solved efficiently, and involves robot motion planning to circumnavigate obstacles. We propose to address this problem with Monte Carlo Tree Search. MCTS is a planning algorithm for sequential decision-making problems. It achieves success in the game of Go, and also well-suited for addressing the challenges in the sorting task. First, it can search in high-dimensional state space by only performing a forward search. This allows to employ commonly available physical model to predict the outcome of actions. Second, it employs an adaptive sampling strategy that focuses its search on the parts of the state space that are relevant to solving the problem. It's particularly important as the sorting task has a large state space and modeling its multiple contact physics is computationally expensive. Third, MCTS requires no explicit target states, but instead can be applied when there is only a discriminative functions to evaluate whether state is a goal. This is the case in the sorting task, where the goal is defined through the relative positions of objects rather than the absolute positions. Before going into more details of MCTS, we define the problem at first. In the planar push sorting problem, a robot is tasked to sort a set of mobile objects in a bounded workspace according to a given class membership. These classes could be user-defined or based on physical properties. A sorted state is a state where the objects of each class form disjoint clusters. All classes have at least some distance from each other and the obstacles. Given an initial valid state, the problem of planar push sorting is then to compute and execute a series of actions that transfer the system from unsorted state to any valid sorted state. An example is given in the above figure, in which the immobile obstacles are rendered with green. Then we adapt the Monte Carlo Tree Search to the sorting task. MCTS is used for sequential decision-making problems with state space, action space, reward signal, and transition model. Given a current state, the algorithm estimates the state action values using simulated episodes called rollout and returns the best action. During rollout, it uses a rollout policy to select actions and simulates state transitions. To focus on high reward regions, MCTS builds a search tree rooted at the current state, with states as nodes and action as edges. With this tree, the algorithm maintains value estimates for the states that are most likely to be reached within a few steps. For every single iteration, the algorithm executes selection, expansion, simulation, backpropagation in sequence, and finally is set to terminate after a certain number of iterations, or through some criterions. Lastly, we model the planar sorting task as sequential decision-making problems for MCTS. We define the robot-centric action space with discrete actions, as depicted on the right. The full configuration space is used as a state space. The updated state is set as a root node to initialize a new search tree for selecting the next best action. Then the sorting planar scheme is formed for sequential decision-making. For the transition model used in expansion and simulation phase, we implement a simulator based on both 2D. It's a 2D physics engine for games like Angry Birds, capable of modeling multi-object interactions. We model the planar push sorting as a deterministic process. The errors in the physics modeling is compensated by replaning after each action. With our action space, it often takes up to 200 transitions until a sorted state is reached. It makes a large number of full rollouts with the physics simulation practically intractable. For this reason, we use truncated rollouts of limited depths. This means that we cannot use previously defined discriminative function as a feedback signal. Therefore, we define a different reward signal Gx that provides useful feedback also for unsorted states and increases when the states become more sorted. We construct a reward signal for a state tax from four components, in which each cluster is modeled as a Gaussian distribution centered at the mean position of that class of objects. The term E self increases as objects of class Ci are more compact. The term E other increases as the center of class Ci and Cj are moved apart. Similarly, the terms E obstacle increases as the center of class Ci is moved away from obstacles. It eventually reaches higher value for more sorted states. Therefore, by maximizing the reward signal, our planner will gradually aggregate objects of the same class and separate those from different classes. By using the reward signal, the search tree sorts each node's visitation count and estimates the upper and lower bound of the reachable reward from its state. Selection and expansion are executed with the tree policy. Simulation is executed by the rollout policy with truncated depths. After each time of rollout, we increment the visitation counter and update the bound estimates for each traverse node in the search tree. The tree policy balances between exploration and exploitation in node selection. Our state action value Q is derived from UCB formula but modified for a deterministic model. The rollout policy starts from a completely random policy to guarantee probabilistic completeness. Finally, the sorting planner outline is formed. Starting from an unsorted state, our sorting algorithm repeatedly runs MCTS to obtain the best action for each state, executes the action, and observes the results. This process is illustrated in the figure and the pseudocode. Although a completely random rollout policy guarantees probabilistic completeness, it's much more simple effective to select actions in an informed way during simulation. For this reason, we learn a rollout policy from the successful sorting experiments to map the states to the probability distribution of the actions. To produce the label training data, we run our push sorting planner with random rollout policy for sorting cubes with one static obstacle random placed in the scenes. We record observed transitions for each solved sorting problem to form the dataset. Then we train the policy model with cross-entropy loss. The training target is the probability distribution over actions, which results from normalizing the state action values. Then the learn policy is employed by the MCTS to improve sampling efficiency. We show the performance of the proposed sorting planner with quantitative and qualitative results. We first conduct experiments to motivate the choice of MCTS and compare against several baselines. We query all algorithms to solve cube sorting tasks with different numbers and classes in simulation. All results are reported by the overall success rate from running 100 trials for each task, together with the mean and standard error of the step numbers. Here we show the qualitative results of sorting different numbers of objects and classes. Next, we require the algorithm to sort scenes containing cubes and non-convex U-shaped objects. The U-shaped objects can easily entangle or trip a cube, which makes it hard to rearrange these objects. The results indicate the algorithm can well handle this case. The success rate is not largely influenced by the step number growth. Here we show the qualitative results of sorting non-convex objects. We compare learned robot policy and the random one in the third experiment, sorting cubes in the presence of multiple immobile obstacles. These are the most difficult problems as it's hard to recover from pushing an object too close to an obstacle. Recall that the learn policy is transformed sorting cubes in scenes with only one immobile obstacle. The results indicate that the MCTS with the learn policy successfully generalized to problems with more obstacles. Further, the more obstacles, the greater is the benefit of using the learn policy over the random one. Here we show the qualitative results of sorting objects in the presence of immobile obstacles. In our last experiment, we evaluated algorithm's performance under modeling error in the physical parameters. We first performed experiments in simulation by adding Gaussian noise on the contact fraction coefficient between objects and the ground when simulating an action execution. The results show that the noise has little effect on the success rate in most cases. However, an increase in the average number of actions needed, which indicates error-correcting behavior. Lastly, we run the planner on a real ABB Yumi for two test cases. Due to hardware limitations, the workspace in real robot experiments is significantly smaller than in simulation. The results are compared in the table. Well, in simulations, we observe very few failures for these test cases, but we observe more on the real robots. All failures on the real robot occurred due to pushing a cube out of bounds. This clearly highlights a vulnerability against uncertainty in states close to the boundary. As long as cubes are well within the workspace, however, the closed-loop approach compensates for modeling errors. Thanks for watching. If you are interested in this work, please refer to our paper and project page for more details.